In this video, we're going to talk about local or relative extreme values as opposed to absolute extreme values that we talked about in the last one. And we're also going to find out how to find these things analytically, which means without a graph. The definition of a local maximum as opposed to an absolute maximum is that it doesn't have to be the absolute highest point on the entire graph. It just has to be higher than everything else nearby. So if we look at this top point over here, that's the absolute maximum because it is the highest point on the whole thing. But right over here, we have something that's a high point. It looks like the top of a hill. It's just not the highest hill on the entire function. So we call that a local maximum. It's greater than every other value nearby, but it's not the single greatest value. Same thing happens with minimums. So we have the absolute minimum over here because that's the lowest point on the whole graph. But we have two local minimums. The first one happens right here where you have the bottom of a valley sort of. And we have another one right here at this endpoint because it's lower than everything else nearby it. It's just not the lowest point on the graph. Absolute minimums are included in local minimums. So if you make a list of all your local extrema, the absolute extrema will be in there. So if you have an absolute max or an absolute min, you can also call that a local max or a local min. Finding extreme values requires first finding what we call critical points or critical values. Critical points are the places where the derivative is 0 or the derivative does not exist. Those are your critical points. Extreme values could occur at critical points or they could occur at endpoints. So there's two types of things that we need to check to find our extreme values: critical points and endpoints if you have them. We don't always have endpoints, but if you have them, you got to check them. There's going to be sort of 3 steps to this process. The first step is to find the derivative, because we can't figure out where the derivative is 0 or where it doesn't exist if we don't know what the derivative is in the first place. So the second step will be to find the critical points. And this means solving 2 different types of equations. We need to solve where is f prime of x equal to 0, and where is f prime of x undefined. Step 3 will be to take that list of critical points and analyze it. You're going to take your list of critical points and also endpoints and analyze it to determine which ones are maximums, which ones are minimums, or it's possible that some of them are neither maximums or minimums. So critical points and endpoints. Okay, we're going to practice it with this function. The directions here say use analytic methods, and so that means no graph. We don't know off the top of our heads what the graph of this function looks like, and we're not going to look at it. We have to try to figure this out algebraically without graphing it in our graphing calculator. So this is sort of a no calculator problem, but we might pull the calculator out at some point just to help us with some of the arithmetic when we start plugging in numbers to find y values. The idea here is you're going to only use the home screen of your calculator, and that will be considered analytic methods as opposed to graphing. So step 1 is to find the derivative. The derivative of this function, this is x to the -1, so the derivative is going to be negative x to the -2. And the derivative of the natural log of x is 1 over x. So that's the derivative of my function. Step 2 will always be easier if you have just one big fraction. So just a note here, we want to try to simplify until we have just one big fraction. So I'm going to rewrite this as -1 over x squared. And then I'm going to get a common denominator. So instead of 1 over x, I'm going to write x over x squared. So now my derivative can be -1 plus x over x squared. Now the reason that that's going to be so much easier is because in step 2 for finding critical points, we need to solve where is y prime equal to 0. And that just requires the numerator to be 0. Because if a numerator of a fraction is 0, then the entire fraction is equal to 0. So we just have to solve -1 plus x equals 0, which means x equals 1. There's our first critical point. We also need to figure out where is the derivative undefined. And that will just require the denominator being 0. As long as you've written your derivative so that it's just a numerator over a denominator, and it's not two separate fractions being added together, then you can split it up like this. Just set the numerator equal to 0 to find where the derivative is 0, set the denominator equal to 0 to figure out where it's undefined. So that would be another critical point. The next thing you want to sort of consider is the endpoints. And they gave us an interval here so that we have endpoints. The thing to notice this time is that that interval only goes from 0.5 up to 4. So this 0 is actually not going to be considered in this problem because it's not in that interval that we're interested in. So we have 2 endpoints and only 1 critical point. Step 3 is going to be the analysis portion. We want to figure out y values that go along with each of these things. So we're going to say if my original function was y equals 1 over x plus the natural log of x, we're interested in 0.5, 1, and 4. If I have maximums and minimums, they are definitely going to be in that list of those 3 numbers. So I'm going to use my calculator to help me figure out what y values go along with those things. So 1 over 0.5 plus the natural log of 0.5. And I get those 3 numbers. So this is a 1.307. Remember, in AP Calculus, we always use 3 decimal places if we're going to round. And this one was 1.636. So now we can kind of do our analysis. We know that the maximums and minimums are in this list. So whatever is the highest y value, that's your absolute max. Whatever's the lowest y value, that's your absolute min. We know that those are guaranteed to exist because this function had endpoints, and that's what the extreme value theorem told us. If we didn't have endpoints, we'd have to be a little bit more careful here. This last option might be a relative maximum or a relative minimum, and in order to determine that, we kind of just want to think about what this graph looks like. So here's 1. This is a 0.5, 2, 3, 4. So we had 1, 1. 0.5 is a little higher than that. And at 4, we had a point that was also just a little higher than all that. So the general shape of this graph is something like this. Since that y value for 0.5 is a little higher than the y value at 1, you know that it can't possibly be a local minimum since it's higher than something else that's close to it. So we would be calling that a local maximum. So if all you needed to know was where the absolute maximums and minimums were, you can stop after just finding those y values. But sometimes we have to analyze all of them in order to see what's going on and talk about local maxes and mins also. And so for this particular problem, that's what I would do. In the next problem, we're going to look at something a little bit more involved to determine if you don't have enough information like that. But this one was pretty easy to just think about what that picture looks like and determine that we've got a local max on each end, and we have a local and absolute minimum in the middle. All right, let's look at another problem. In order to take a derivative for this, I'm going to rewrite it so that it looks like a chain rule problem. So this is going to be a power of -1/2. Step 1 is to find the derivative. So y prime, I'm going to use the chain rule, bring down the -1/2, keep the inside the same, subtract 1 for a new exponent, and then multiply by the derivative of the inside. So -2x will be that derivative. And then it turns out this -1/2 and this -2 will cancel each other out. So my derivative will be x over 1 minus x squared to the 3/2 power. And that's just one fraction exactly the way I wanted it to be. So step 2, my critical points will be x equals 0, and then set the denominator equal to 0 in order for this to equal 0. That inside part will have to equal 0, which means x squared will have to be 1. So we could have plus or minus 1. So we have critical points, and this time they didn't give us endpoints. So we need to sort of think about what the domain is for this function on our own. Remember, when you're thinking about restrictions for the domain, you need to consider anything that might give you a negative under a square root is off limits. Anything that might give you a 0 in the denominator is off limits. So in this case, anything that gives us a non-positive number underneath that radical is going to be off limits. We just sort of figured out that if x is 1 or -1, it's going to give us a 0 in there. And if x is anything larger than 1 or -1, it's going to give us a negative under square root. So in this case, x has to be less than 1 and not equal to 1, or and x has to be greater than -1. So we can only look at numbers here that are in between -1 and 1. Anything else will give us either a 0 or a negative under that radical, which we can't have. So when we talk about critical points being -1 and 1, we can't actually have those as critical points because they're not in the domain. So this time we actually only have one critical point, and that's actually going to make it more challenging because we don't have anything to compare it to. We can plug 0 in and figure out that the y value there will be, let's see, 1 over 1. Yeah, 1. So this is the point 0, 1. But we don't know, is that a high point or a low point? We don't have anything to compare it to in order to figure out if that's a local max or a local min. The other thing to consider is the extreme value theorem is not going to apply here because we don't have endpoints. So we're not guaranteed to have an absolute max or an absolute min. We might or we might not. So we need some other strategies here in order to do the analysis portion. We have this point, 0, 1, and nothing to compare it to. We need to figure out, is this higher or lower than the points around it in order to call it a max or a min? So we're going to build what we call a sign chart. A sign chart is essentially just a number line. We're going to put X values on the bottom, and we're going to talk about derivative values on the top. So we're going to forget about that 1 for a while. This is just X equals 0. I'm going to put X equals 1 down here, actually -1, and I'm going to put X equals 1 up here to remind us that we're not interested in anything beyond those, but we also need to remember that these themselves are not defined. We're just going to be looking at the interval between them. So what we want to know from this sign chart is the derivative of this function positive or negative on this interval? So we're going to imagine plugging in a number that is in between 0 and -1. We're going to plug in some small negative number to the derivative. So if I imagine plugging in like a -1/2 into that derivative, then it's going to say -1/2 over y minus -1/2 squared over, or raised to the 3/2 power. So that'll be -1/2 over 1 minus a fourth. So 3/4 raised to the 3/2 power. And I don't need to know what that is in order to figure out that it's going to be negative, because I have a negative number on the top and I have a positive number on the bottom. So I don't have to go any farther with this. All I'm interested in knowing is that it's negative on that interval. And if it's negative at -1/2, it's going to be negative on the entire interval from -1 to 0. Because I know when x equals 0, the derivative equals 0. So next I want to know, what if I plug in something like a half? Well, then this turns into 1/2 over positive 1/2 squared. That doesn't change anything on the bottom since it was getting squared, but now in the numerator, I'm going to have a positive number, so that's going to end up being positive. So that tells me that everything in between 0 and 1 has a positive derivative. That work primarily happens in your head. We don't really need to know what the y values are, what the derivative values are at those points. We just need to know, is the derivative positive or negative at those points? So up above my sign chart, I'm labeling it with the sign of the derivative. At the bottom of your sign chart, you're labeling it with x values. So what this tells me is that my original function, y, not y prime, my original function y is decreasing and then increasing. Because if the derivative is negative, that means the original function is decreasing. And when the derivative is positive, that means the original function is increasing. So y looks like this. And that is what helps us figure out that at x equals 0, we have a minimum and not a maximum. It is a local minimum, but since we figured out it's increasing, it's going up in both directions, that means it's also the absolute minimum. So we kind of just did a little analysis to figure out what this function looks like. It's going to decrease and then it's going to increase, and it's going to have open circles on either end where it stops being defined. So it's not that it's continuing up forever. And so we can't say we have a maximum there because of those open circles. So your answer in the end, we have a local minimum at the point 0, 1. Now let's go back up and look at how this question was phrased. It says, find the extreme values and where they occur. That kind of sounds like two different questions, so we're going to answer it that way. So the minimum value is 1, and it occurs at x equals 0, and there is no maximum value. So we're kind of talking about local minimums and local maximums and absolute minimums and absolute maximums all at the same time here. You just need to pay attention to how the question is phrased to know which piece of that you really need as the answer to your question each time. Something to watch out for here is that sometimes when you make a list of your critical points, you will get points in there that are critical points that are not maximums and minimums. So this is like it's a statement that doesn't work both ways. A function's extrema can occur only at critical points or endpoints, but not every critical point or endpoint signals the presence of an extreme value. So we can say, if it's a local maximum, then it's a critical point, but we can't say if it's a critical point, it's definitely an extreme value. So here's a classic example. If we have y equals x cubed, that point right there in the middle, 0, 0, is a place where the derivative will be 0. So this is a critical point. But it is obviously not an extreme point. A sign chart would help you figure this out, because if we made a sign chart for this point, we would find out that the derivative is positive to the left of that point, and it is still positive to the right of that point, because that function is increasing the whole way. So if you find that the derivative doesn't change from increasing to decreasing or vice versa, that means that you don't have a maximum or a minimum there. Now, we did that just by looking at the picture, but if you were to actually figure out what is the derivative of this, then you can see why this is all happening. The derivative is 3x squared, and that derivative function is going to be positive no matter what because of the x squared in it. Okay, one more problem here about finding critical points and extreme values, and this is a piecewise function. Anytime you have a piecewise function, your question should be, what is happening at the place where it breaks? So what is happening at x equals 1? We want to know, do those two pieces connect there? And we also want to know, is the derivative the same coming from both sides? So is it continuous at x equals 1? Is it differentiable at x equals 1? That'll help us figure out if we've got critical points happening there. So the first thing I'm going to do is just plug in 1 to both of those functions and see if I get the same thing. So if I do negative 1 squared minus 2x, minus 2 times 1 plus 4, that's going to give me negative 1 minus 2 plus 4, and that's going to give me 1. If I put it in the other function, negative 1 squared plus 6 times 1 minus 4, that's going to give me negative 1 plus 6 minus 4, and that is also going to give me 1. So what this tells me is that it's continuous. I know the two pieces of this function connect. The next thing I want to know is what's happening with the derivative. So just like if you were following our basic 3 steps, first find the derivative and then think about the critical points and then analyze them. I'm going to find the derivative of both sides of this function. So y prime is going to be negative 2x minus 2 and negative 2x plus 6. Now this is for everything less than 1. This is for everything greater than 1. You'll notice that I didn't put an or equal to there because I'm not actually sure what's happening with the derivative at 1 just yet. We need to sort of figure that out. So my question is now, what is going on at 1 with the derivative? I'm going to do the same thing I did up here. Negative 2 times 1 minus 2 gives me negative 2 minus 2, negative 4. For the bottom piece, negative 2 times 1 plus 6 gives me negative 2 plus 6 gives me 4. So that tells me that two pieces do not have the same derivative at the place where they connect, so it's not differentiable at x equals 1. So I'm not going to put an or equal to on there because the derivative doesn't exist at x equals 1. So that tells me that wherever they connect, it has a sharp turn, a corner or a cusp, because the derivative is suddenly changing from negative 4 to 4. The slope is suddenly changing from negative 4 to 4. So it's suddenly at some sort of corner or cusp changing from decreasing to increasing. All right, next step is to find critical points. I want to figure out where is my derivative equal to 0. So I could say negative 2x minus 2 equals 0. Solve that. You find out x could be negative 1. That's one of my critical points. Negative 2x plus 6 could be 0. Solve that. X equals 3 is a critical point. The other thing that gives me critical points is where the derivative is undefined. And undefined doesn't always mean that there's a 0 in the denominator. In this case, we have a place where the derivative doesn't exist because we found that at the place where this piecewise function breaks, there's a corner or a cusp. So the derivative is actually undefined at x equals 1, which we determined above. So that is one of your critical points. Step 3, we're going to analyze this information. Analysis sometimes can start with a table. Sometimes you can get a lot of information just by making a table. So negative 1, 1, 3. Let's see, we don't have any endpoints here. And the domain is going to be all real numbers because the domain of both of those pieces of that function is all real numbers. So it's going to keep going in both directions. So we don't have any endpoints to look at, and that means we're not necessarily guaranteed to have a maximum or a minimum, and that's important to know going in here. So whenever we find the y values that go along with this, we can't just automatically assume that the highest one is an absolute max and the lowest one is an absolute min. All right, negative 1 and 1 and 3. I'm going to plug those into the original function in order to find the y values that go along with them. Now, I already plugged 1 in, and I got 1, so That one's easy. If I plug in -1, I'm going to have to use the top piece of this because -1 is less than 1. So I'm going to do -1 squared minus 2 times -1 plus 4. And you can probably pull out your calculator for this, but I think this is fair game for making you do without a calculator on the AP exam. So just be prepared. You may need to do some arithmetic like this by hand, but if you're just trying to save time while you're doing your homework, I think it's reasonable to pull your calculator out to help you with something like this. All right, next I'm going to plug in 3, and this time I have to plug it into the bottom function because that's bigger than 1. So I'm going to do -3 squared plus 6 times 3 minus 4. So that's 9 minus 4, that's also 5. So I have my y values. You have some that are higher and some that are lower, but it's important to know we're not really guaranteed anything about this. There might be no absolute extreme values. So we can kind of think about what it will look like at 1, 1, 3, 5, -1, 5. But just having that information doesn't give me a lot of confidence to know what this function is going to look like. It looks like that point at 1, 1 will be a minimum, but I'm not really sure about the other ones yet. Like it could be something like this. It could be something like this, or kind of any other of a million different options. So we're going to make a sign chart in order to figure this out. I'm going to put x values on the bottom, and my important x values are -1, 1, and 3. And I'm going to put derivative signs on the top. So it's important to make sure you're looking at the derivative, not the original function for this. So imagine plugging in something from this interval here, from anything from -infinity up to -1. I'm going to plug it into my derivative. So I have to use the top portion of this derivative here. I'm going to plug in something like -100. If I plug in -100, I'm going to get -2 times -100 is +200 minus 2 will still give me a positive number. So that means everything on this interval will give me a positive number. For the next interval, I'm going to plug in 0. And I'm still going to use that top piece of the derivative function because 0 is less than 1. I'm going to get -2. So that means everything on this interval is negative. And then I'm going to plug in probably 2. This time I'm going to use the bottom function because this is a number that's greater than 1. So if I plug in 2, I get -2 times 2 plus 6. -4 plus 6 gives me 2, positive 2. So that means this is positive. And then if I plug in something bigger than 3, anything from 3 all the way to infinity. So with those situations, I like to just go ahead and plug in something gigantic, like a million. If I plug in a million, I have -2 million plus 6. It's definitely going to be negative. You don't even really have to do the calculations to know it's going to be negative if you use a gigantic number like that. So now I can tell I have my original function, y, is something that increases and then decreases and then increases and then decreases. So between -infinity and -1, it's going to be increasing. Between -1 and 1, it's going to be decreasing. And remember we said the derivative doesn't exist at 1, so that's going to be a sharp turn. Then it's going to increase again, and then it's going to decrease again. This needs to be a sharp corner because the derivative doesn't exist, But at the tops here, the 3, 5 and the negative 1, 5, those need to not be sharp turns because the derivative does exist there. So we end up with something that looks like McDonald's arches, like an M. We could have probably figured this out using what we know about algebra, because our original piecewise function was an upside down parabola connected with another upside down parabola. So that's what this looks like in the end, is one parabola that gets cut off and then another parabola begins. And it's going to go forever in both directions. So to actually answer the question here, we have an absolute max at 5, and that occurs at x equals negative 1, and again at x equals 3. So those 2 points tied for absolute max. One maximum value occurs in 2 different places. And then we have a local minimum. The value is 1, and it occurs at x equals 1. And there is no absolute minimum because this goes down in both directions. And we weren't guaranteed to have an absolute minimum because the conditions of the extreme value theorem were not met here because we don't have any endpoints. Okay, use this to help you with some of the practice from the extreme value practice before this, and also the local extreme value practice, and then go on to the next video.